Welcome to lecture 20. So do we have any questions from previous times? Anyone?
No, sir.
Okay. So let me just recap a little bit. So last time we were talking about, I wanted to motivate motivating the unitarity theorem, right? But before that, I reminded you of a result for finite groups. So for finite groups, if we have a function f of the group element, then if I sum over all the group elements, that sum is unchanged if we change the argument of the function by right multiplying by a specific group element G prime, or by left multiplying by a specific group element G prime. Okay, so it doesn't matter what G prime is, as long as we do the sum over all G. So this sum doesn't change. Okay, and so there is a continuous version of that for compact groups. For compact groups, this result doesn't hold for non-compact groups. So here, basically, the finite part becomes replaced by the compact part. And for compact Lie groups, the sum over all the group elements get replaced by something called the Haar measure. And the Haar measure is a canonical measure that you can define on the group element, okay? On the group, on the Lie group. So it's a canonical measure, meaning that there is a well-defined prescription for defining that. So then this theorem gets generalized to the theorem that the integral over the whole group using the Haar measure with some integrand, which is a function of the group element, that thing remains invariant if we change the argument by right multiplying by some specific element of the group, or if we left multiply. Right, so this is actually intuitively, it should not be a very hard thing to understand. And why that is so, let me just tell you why. So suppose this is my group, so G. So it could be a discrete group, it could be a compact group. So, and if I have some function, suppose that the function takes some value in some range. So as I do the integral over the whole group, what I'm going to see is that the result of that is that so this is mapping us to how should I let it be a real function, right? So this is some real function, some real line, and the function is mapping us here, say from here to here, and the function is mapping us somehow like over here. And we end up, let's just let us just take for the sake of simplicity a monotonic function. It doesn't have to be, just just for visualization. Then basically what we're doing is that when we integrate over this whole space, we are essentially evaluating this length, right? That's what this integral is saying. And now, if I now multiply by, say, G prime, what we're doing is that, we are just changing the point at which we started the integral. This could have been the initial point, but if we multiply by G prime, our initial point becomes this point. But the range of integration is the same, because we're integrating of the whole group. So eventually, we are basically just going to be evaluating the same volume, right? So this is very intuitively, it's easy to understand intuitively, okay? So this is a useful lemma that we shall use in proving the unitarity theorem. Okay, any questions? Okay, so because we have quite a few mathematicians in the crowd, so I wanted to motivate why unitarity is important in group theory. So before we discuss the unitarity theorem, the motivation is the following. The motivation is from quantum mechanics, okay? In quantum mechanics, states of a physical system, we write it as in this symbol. It just means a vector. It doesn't mean any other, you don't have to worry about why this so-called weird notation is called a ket, if you want to know. So the state of the system is part of a vector space, H, and this vector space is called a Hilbert space. And the Hilbert space is a space which has an inner product, has a positive definite inner product, which means that for every psi, or for the vector space psi, there are these dual vectors, which I'm calling phi, such that there is an inner product. So this is a complex number, okay? And the positive definiteness of the inner product means that if we take that for every phi, there is a dual such that this is a real number, and we can normalize it to 1. It doesn't have to be, but we can normalize it to 1. And yeah, and so this is what it means to have a positive definite inner product. In physics, the basic observables, in physics are the square of these guys. They are essentially, they're complex numbers, so you can take the modulus and square it. And these guys have, like this thing has the interpretation of probability, and that's why we usually normalize it. It is somehow saying that the probability of everything happening is 1. The sum of probability of everything happening is 1. So now if I make a change to the system, something changes on the Hilbert space. So we do make some transformation on the system, and the state will become some other state, say psi prime. So the Hilbert space is a linear vector space, so psi prime will be related to psi by some linear operator. But if now, suppose that this operation that we did is a symmetry, that L represents a symmetry of the system. Okay, it could be a time symmetry, that the system does not depend on time, or it could be that the system does not depend whether you translate the system in space. It could be many other things. We don't care exactly what it is. But if L is a symmetry, then of course, the probabilities associated with it, the observables, should not change. That means that under this transformation, inner products like these should remain invariant. So if psi changes to psi prime, so L acting on psi, and phi changes it to phi prime, with L acting on phi, then the inner product of phi prime of psi prime. So this, the way we go from this vector space to its dual is by taking the Hermitian conjugate. So this prime is going to be this guy, L dagger. Okay, this is the Hermitian conjugate of that. So under this transformation, this thing becomes psi phi becomes phi prime, but this thing is phi L dagger, and this thing is L of psi. So this needs to be equal to this, and that is only possible if the linear operator satisfies this. In other words, that the linear operator is unitary. Okay. So transformation that we make on our system are implemented on the Hilbert space by unitary operators. And therefore, unitary representations of groups are important. Okay, shall I write that down? Because it's an important lesson. So the physical transformation on a system induce unitary transformations, I should say unitary linear transformations on the Hilbert space that represents the space of states, or wave functions, sometimes they're called, of the system. This is why unitary representations of groups are so important. Okay, is that clear, the motivation?
Yes, sir.
Okay, anyone else who wants to ask any questions? If it's
Sir,
not...
I have a question. So
yes, please.
You're talking about unitary representation of the group. So like, can all groups be essentially represented in unitary manner? Like physical systems.
Yeah, that's going to be the key to the unitarity theorem. Yes. So yeah, Nahib raised a very good point, and let me just state the unitarity theorem as the result. Okay, as an answer.